Hello friends, welcome to the next lecture. Today we will look at how to calculate the energy density of the particles in the early universe. We will look at relativistic and non-relativistic scenarios. So let us look at first of all the relativistic scenario, that energy density of particle is equal to the corresponding antiparticle and is given by this expression. The calculation is pretty straightforward. We just plug in the values in this energy density expression. For in the relativistic regime, energy is given by P, momentum, and Fp is given by this expression 1 over E to the power P over T plus minus 1. Because we are assuming temperature much greater than mu, so mu term is not here. We have seen this in our previous videos also, that in the relativistic regime Fp takes this form, and then we get I think there are some mistakes here. Okay. I think I don't need this statement. Do I? No. Okay. Sorry, I had to do some cleanup here. Yeah, so this is an expression for energy density, and it's pretty straightforward. For plus one is the fermion integral, for fermion, and this is the integral for bosons, and EF is the energy density for fermions. Energy density fermions, and this is integral fermions, and energy density bosons. Okay, so leveraging the power of Mathematica, and let me mention here that I am going to use Mathematica to solve the integrals. In case you are wondering what am I doing here, if you have not watched my previous videos. In previous videos, in the last video, I calculate number density using the similar Mathematica commands. So I'm using the same technique for now energy density, and it's all simple setting up integrals and simplifying, and you can see that once you run it, you will get this expression for energy density fermions, this expression for energy density bosons, and so again, everything pretty straightforward. You factor out g pi square T4 by 30. For bosons, we get 1, and for fermions, we get 7 by 8. For relativistic fermions, as we have seen in our last video, that for relativistic fermions, the difference in number densities gives us exact expression if we do not neglect the chemical potential, keep the chemical potential term. We get the exact expression for the difference in number densities between the particle and antiparticles. Now, if we sum up the energy densities of particles and antiparticles, we will see that we will get the exact expression. Again, the technique is the same which I used in my last video. Just set up the integrals first. And after you set up the integrals, plug in the value of Fp for the fermions. This is Fp for fermions, and we are in the relativistic regime. So Ep approximates to P and Ep approximates to P, but keep chemical potential. Do not drop chemical potential term. And then sum up these two integrals, integral 1 and integral 2. You sum up these two integrals, and rest is pretty straightforward. We have seen this in last video. So integral 1, integral 2, you sum up, you get this sum, and then you expand it using a series function. First, I would substitute this mu over t. I would replace mu over t with x, and then I do, because mu over t approaches 0, is approximately equal to 0. So I would expand it around x is equal to 0. After expansion, you see that only 3 terms survive, even though I am expanding up to 10 terms, but I see that only 3 terms survive. So you can see that even if you try to get more than 10 terms up, like up to 20 terms, you see always 3 terms survive. So what I need to do now is that in order to get this terms, the 3 terms which survive, I would only the terms up to x to the power 4 survives. So I would say that give me series expansion with x to the power 4. And again, this normal command I am using, because if I don't use normal command, then you see that I get one additional term here. I think I need to rerun all this. One second. Integral 1 is this. Integral 2 is this. Sum is this. And then I get this. Run this. And now you run this. Sorry, because I restarted my computer, and these variables do not contain anything, and that is why I was not getting proper results. So what I need to simplify this. Yeah, simplify this and simplify this. So I have so when I simplify, I need to say that x yeah, so integer sum 4 is this, and yeah, so what I want is that I do not want this extra term, and because I do not want this extra term, I would say normal. And if I say normal, I get rid of that extra term. Like if I don't say normal, and you see that I'm getting this order of x to the power 5, but now I do not, now I use the function normal. Now that order of x to the power 5 is gone, this is what I need. And then I would simplify, and I get this. Now I will use the previous function which I showed you in my last video, which was a custom return function, in order to factor out a certain part from an expression. I wrote a custom function factor. So it has two arguments, that you write the expression and whatever you want to factor out, and then you can use this function to factor out some term from an expression. So whatever term I have got here, now I want to factor out 7 pi square t4 outside, which means from this whole I want to factor out 7 pi square t4 g over 120. So when I do that factorization, when I factor out that term using that custom function, I get this. So the total energy, sum of energy contribution from particle and antiparticles of a given species is given by this expression. Everything is pretty straightforward. Some Mathematica commands may be new for you, but I like using Mathematica for solving problems. So wherever possible, I will heavily use Mathematica. Now the next thing is that for the non-relativistic, where temperature is much smaller than mass, prove the following. Okay, everything is pretty straightforward. Now, what is energy density? We have seen in our previous videos. What is energy? Not energy density. What is energy? Energy is given by this expression, m plus p square over 2m in the non-relativistic regime, and Fp is given by 1 over this expression, e to the power m plus p square by 2m minus mu over t plus minus 1. Everything is straightforward here, and this plus minus 1 is no longer needed in the non-relativistic regime because the exponential term is much greater than plus minus 1, so we can drop this plus minus 1. And again, plug in the values in the integral. This is the Mathematica command here. Simplify, and you get this. So after a bit of Mathematica, this cleanup, so you see that energy density acquires this expression, and when I divide energy density of a non-relativistic divided by number density of non-relativistic, this number density non-relativistic is a variable which was calculated in my last video. Yeah, so you see in the last video I had this variable number density non-relativistic, and now I calculate energy density non-relativistic here, divide by number density non-relativistic, and I get m plus 3t by 2. So energy density non-relativistic is equal to m plus 3t by 2 times number density non-relativistic. And because mass is much greater than temperature in the non-relativistic regime, so this is approximately equal to nm. M plus 3 by 2 is approximately equal to m, so the whole expression becomes nm. Okay guys, now the next part, D. Is there any D part? No, there's no D part. So why do I have it? Why do I have something D here? Blah 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 blah. I think that is for my next video. Or should I do it in this video? Oh, I will do it in next video, the part D. Yeah, I think that deserves a separate discussion. I am doing some gymnastics here using solving integrals numerically. And yeah, for this video, I think up to these 3 parts A, B, C are sufficient for this video. Thank you very much. See you next time.